Good evening, everybody. Welcome you all to the second lecture of our Advanced Material Chemistry course, and we are covering the General Materials Chemistry part. So, just spending 2 minutes on what we did last time was we studied about what is unit cell, what is lattice, what is Bravais lattice, what are seven crystal systems, and the simple things like what are the specific criterion for a lattice to be called as Bravais lattice. Okay. Today again we'll do some of the simpler concepts that you would have done earlier. But what we'll try to do is maybe spend little time on the things that I would feel that you would have done earlier, and maybe a little more time on things that you would have done earlier, but maybe that particular things a little more clarification. Okay. So again, coming on to when we talk about crystal structure, all of us record XRTs. Those of us who do, there is something called lattice planes. So what is a lattice plane? Lattice plane, as all of us know, it is basically a concept. Okay. Now we say that these are the plane of atoms, but obviously a crystal, a unit cell does not know that it has planes of atom, right? So it is only for our understanding the concept of lattice planes has been introduced based on unit cell shape and its size. So what it does is it basically tells you, okay, these are the number of the atoms that are arranged on this particular plane. These are the number of the atoms that are arranged on 100 or 110 or 11 cell, 11 lattice plane. So what it does is it provides you a reference grid to which you can actually refer the atoms or the ions in a particular unit cell. And these lattice planes are characterized by interplanar spacing d. For example, we say that the 100 planes are separated by d, which is actually nothing but the lattice parameter A of the cell. Okay. And again, all of you very well know that lattice planes are labeled by set of three numbers, which we also call as H, K, L values. And these are specifically named as Miller indices. So basically, what Miller indices tell you? Miller indices tells you the plane that we are talking about, how it intersects your X, Y, and Z axis. How do we determine Miller indices? Most of you would have done it, but just for the sake of completion, let me just go through it. What you do is you consider a cube as shown on the right hand side with the cell dimension A. Since it is a cube, it is A, and A. So along the three axes, the lattice parameter is same. Now, suppose I want to determine what are the Miller indices of the plane that is shaded pink in this left-hand side figure. Okay, so for this, what we do is we try to understand what is the intercept made by that particular plane on x-axis, on y-axis, and on z-axis. Like this red shaded plane, it makes an intercept of A on x-axis, but it is parallel to y-axis and z-axis. So the intercept made on y and z-axis are infinity because they are not intersecting them. So basically the coordinates are 1, infinity, infinity. So once we know the value of the intercept, we take the reciprocal. In this case, it would be 1, 0, 0. But suppose it was half 0, 0. Like suppose we have any number which has got a denominator, then we multiply all the three intercepts, all the three numbers by the denominator to get the whole number, and that gives us the Miller indices. For example, in this particular case, the shaded plane, I will repeat once again, makes an intercept of A on x-axis. It does not intersect y-axis and z-axis. So the intercepts are infinity, infinity. It is A, infinity, infinity. And since A is the lattice parameter, so the intercept made is 1. Okay. So 1, infinity, infinity. Take the reciprocal, you get 1, 0, 0, which is the Miller indices of this particular plane. In fact, if I show you this cube, and you imagine any of the corner as the origin. Let's say I assume this particular corner as the origin, then all the faces of the cube have got the Miller indices as 1, 0, 0. Okay. And there are certain rules that you need to follow when you write the Miller indices. They are denoted without any comma and you put them in the small bracket. In case you have equivalent set of plane. Now what do you mean by it? Suppose you have a cubic system. In a cubic system, A is equal to B is equal to C. That means your three lattice parameter I can also denote as A. That means the lattice, if I say the intercept of 1 on A will be equal to intercept of 1 on B, but and this will be equal to intercept of 1 on C. But if A, B, C were not equal, then 1 on A had different meaning than 1 on B and it would have had different meaning than 1 on C. Okay. In this case, the three axes are unequal. But when I'm talking about the cubic system, all the three lattice parameters are same. So 1 means 1 on A is equal to 1 on B is equal to 1 on C. Then your lattice planes 1, 0, 0, 0, 1, 0 and 0, 0, 1. Okay, if this was the origin, then the plane that is pointing towards me is 1, 0, 0. This particular plane is 1, 0, 0, 1 and this particular plane is 0, 1, 0. Then all of them belong to a family of plane. They are equivalent plane and we denote them by curly bracket and we just write any one of it. Let's say we write 1, 0, 0. We could have written 0, 1, 0. But the point that I want to make is that they belong to one family and they can be denoted by a single Miller indices covered by, like encapsulated by curly bracket. If you have a negative Miller indices is nothing. Suppose your origin was this and I was talking of a plane here. Okay, because the unit cells are anyway arranged three-dimensionally in all the three directions. Suppose if this is +1, then this would be -1. So I hope I'm clear. So when you have a negative Miller indices, you simply put a bar on the number. And of course, as I said, the Miller indices are characterized by their interplanar spacing D. So each set of plane has got a specific interplanar spacing. Okay. Now let's try to find Miller indices for following planes. I'll give you 1 minute and you try to do it on your own. And then maybe you can write in the chat box for the first one. If I have a cubic system and I draw this triangular plane, what would be the Miller indices of this particular plane? I'll give you 1 minute and try solving. If you can write it, fine, we'll move ahead. Otherwise, I'll help you solve it. Yes, Gunjan has written 111 and she's perfectly correct. I hope all of you have also understood why is it 111. This is because it is making an intercept of 1 on x-axis, an intercept of 1 on y-axis and an intercept of 1 on z-axis. So what you have is 1, 1, 1 and the next step is that we have to take the reciprocal of this which is nothing again but 1, 1, 1 and so we can denote the Miller indices by this. Okay. Similarly for the next set of, can we go to the chat box again? Ankur and Mohit, just one thing I just mentioned in the last slide that these Miller indices are not to be separated by commas. Okay, they are by convention, they are written without commas and to Gunjan as well, they are actually, you have to put a bracket outside these Miller indices. So no commas with the small bracket. Okay, yeah. So for the next set of plane, it makes an intercept of 1 on x-axis, an intercept of 1 on y-axis, and an intercept of infinity on z axis. Taking the reciprocal, we have 1, 1, 0 and 1, 1, 0. And then of course, when you take the reciprocal, it will come out. Okay, we have already taken the reciprocal and there is nothing in the denominator, so we don't need to multiply it. So the Miller indices of this plane is 1, 1, 0 and with small brackets. Okay. Now, most of the time we also define directions in the unit cell. Again, to find directions in the unit cell is another easier task. What you have to do is, suppose any random direction is given in the unit cell and you are asked to label that particular direction. What will you do is, you take that direction and then parallel to that direction, draw a direction which should pass through the origin. Okay. And then one end keep at the origin, but it should be parallel to the direction whose Miller indices you're trying to find. And then once it passes to the origin, you see what is the intersection point of that particular line with x, y, and z axis. Okay, then determine the coordinate of that particular line. Now, in this case, you don't have to take any reciprocal. Simply convert those numbers if they are fractions into whole number. And that would be the Miller indices of direction. So Miller indices of plane use small bracket. Miller indices of direction use a square bracket. Okay. And if you have a family of directions, like you had the family of planes, in that case, you have to use these triangular brackets. Okay. Now, just giving a small example. Let's say in this is you assume, look at this left hand side figure. You assume that c axis is 0 everywhere and I want to find the direction OB. Okay. Now OB is intersecting this particular grid at this point, and for your convenience I've divided into 5 parts in both x and y direction. So the coordinate of the point where it is intersecting this is, on x axis it is basically intersecting at 2 by 5. Okay. And on y axis it is intersecting at 1. Okay. No, y axis it is intersecting at, sorry, x axis it was 1. Okay. The coordinate on x axis is 1. The coordinate on y axis is 2 by 5. And on c axis, as I told you, it is making an intercept of 0 because c axis goes in this direction. Now, if I want to make the whole number of this, it makes it 5, 2, 0. And these are the Miller indices of this particular direction. Similarly, I can find the direction for OA. It is making an intercept of 1 on x-axis, 1 on y-axis, and 0 on c-axis. Now here I do not really have to make anything as whole number because there is no fraction. So this is the Miller indices of direction OA. I hope it is clear. Okay. So this is how you can find the Miller indices for directions. Now coming to the, from this slide onward, we will talk about crystal chemistry. Now the first concept that I want to clarify is, people use crystal chemistry and crystallography interchangeably. Now here at this point, I would want to tell you the difference between what is crystal chemistry and what is crystallography. So when I talk of crystal chemistry, it is basically description or classification of the structure. What are the factors that govern that particular structure? What are the conditions under which I can make that particular structure stable? And what is the relation between the structure and its physical chemical property? So when I study all this, I say I am studying crystal chemistry. But when I'm talking of experimental methods which I can use to determine the structure of my material, then the branch of materials chemistry or solid state chemistry or solid state physics that I'm referring to is called crystallography. Okay. So I hope after now you will be able to distinguish between these two terms, crystal chemistry and crystallography. All right. Okay, now when I say I want to define a crystal structure, okay, every person is different. I can ask you to define, let's say, a cube. you can define in terms of small cuboids, you can define in terms of a bada cube. So there are many ways by which you can define a particular thing. Similarly, we can define crystal structure by various different conventions. First of all is we can define in terms of unit cell. That means suppose you ask me what is the structure of NaCl. I would simply tell you what is the structure of unit cell of NaCl. Where are the atoms placed? Because ultimately, when that unit cell is repeated three-dimensionally, I would be able to recreate the NaCl structure. Okay. So by defining shape, that is telling the lattice parameters, size, shape means whether it is cubic, whether it is tetragonal, size means defining the lattice parameter, and position of atoms. If you tell these things about a unit cell, you are able to define the structure of a material. Or otherwise, there are other ways of looking at the structure. You can define them in terms of close packed structure, which you know, and we will also study in next 2-3 slides, or also as space filling polyhedra. We will talk about these two things as well. The last two things, that is the close packed structure and space filling polyhedra, give you a better idea of the three-dimensional view of how your structure will look like. Okay, close packed structure, all of us know, right from 9th standard, we are told there is a hexagonal close packing, there is a cubic close packing. So I will try to spend little time on it, but on points which I can feel that you might need a little understanding, better understanding on. So when we define the close packing, what is the guiding factor on this? Guiding factor is whatever way you arrange your sphere, you have to see that you should attain maximum density. Okay, so what you do is you consider the most efficient way. How can you are given, let's say here, the blue spheres, which are of equal size, and you have to arrange them in three-dimensional. What is the most efficient way of packing it? Okay, the most efficient way is you arrange the first row as it is shown here, and then in the grooves of the first row, you start placing your second row. This is the groove of the first row. In this, you have placed this sphere. Okay. Then in this groove, you have placed this sphere. And similarly, you place a third row and then the fourth row and so on. This is the most efficient way in which you can pack equally sized sphere in 2 dimensions. Okay. So closest neighbor are in contact. Now this is my first layer. So if you now look at it, there are basically two types of triangular interstices formed. One is this, which are pointing upwards. Okay. And one is this, which are pointing downwards. Right. Now suppose I place my second layer of sphere on the first layer, let's say on the triangular interstices which were pointing upward. Now, mind you, if you look at the second 2D thing, if you have equally sized sphere, then you cannot occupy both the upward pointing and downward pointing interstices. That is because the spheres are equal size and you simply just cannot do that. Okay. Now you place the second layer on this, on either one, the one or the two interstices that I marked in the last slide. Now, when we place the third layer, all of you know that very nicely. If this third layer is placed again on 1, the second layer was placed on triangle marked 1. If I place third layer again on 1, then what you will get is the CCP packing. That is the configuration of layer 1, layer 2, layer 3, and the configuration of layer 1 would be repeated only at layer 4. So it is what we also call as the very famous ABC, ABC, ABC packing. Okay. But if your third layer was placed on the interstices which were marked downward, or in other way, if your third layer of sphere is directly over the first layer of sphere, then what you get is hexagonal close packing, also famously known as AB close pack. Okay, you know all this. Now coordination number in both HCP. What is the coordination number? If I ask you to define it, the nearest neighbor present around a particular atom, a particular ion, or in this case, a particular sphere is called the coordination number. Now, coordination number on both HCP and CCP is 12. How is that? If we see, it has got, if I concentrate on this one, there are 6 in this layer. There would be, because I can occupy only one kind of interstices, 1, 2, 3 in the top layer, and niche, there would be 3 in the bottom layer. Now, if it is a cubic close packing, then if this triangle, if I'm join the center of these 3 circles, if this triangle is marked like this, then the layer which would be at the bottommost would be, and if I join the center of those 3 circles, it would be marked like this. That is, the first layer and the third layer, those triangles would be not eclipsed but staggered. And that is why it is 1, 2, 3, 1, 2, 3 packing. Okay. So as we just counted 6 in the same layer. If I'm concentrating on the center sphere, then 6 in the same layer, 3 on the layer above, 3 in the layer below. 6 plus 3, 9 plus 3, 12. So coordination number in HCP and CCP are 12. Packing density for both CCP and HCP is 74%, and it is very difficult to, it is actually impossible to attain better density than CCP and HCP. That is why most of the metals, they crystallize in either one of these close packing. Now, if you ask me, there are many other packings also available, tetragonal packing or, mixture of CCP and HCP, but they happen only under different condition. Under ambient condition, any material would want to crystallize in the packing which gives it maximum density, and that is HCP and CCP. Okay, so how to calculate the packing fraction, we'll come to it later when we talk about the unit cell of this. Now, here is something that I would want to point your attention. Maybe you would be knowing that, but it is good to revise it. How does the unit cell of HCP looks like? Okay. Now, this is how the packing of HCP is. Okay. This is the first layer. And this is the third layer. They are exactly eclipsing each other. And this is the second layer of atoms. Okay. Normally, the unit cell is defined as 1/3 of this. Okay, one is this unit cell that you can see, this particular. And then one is this. And the third one is this. Okay, so this is how it looks like. Okay, now, when we talk about the unit cell of hexagonal close packing, the basal plane of the unit cell, and when I say basal plane, I say, let's say if this is a cube, even though this is not the unit cell of hexagonal close packing, these are what I call the basal planes. Okay, the basal planes, they coincide with the packed layer. Like we showed the packing of the layer in the previous slide, layer 1, layer 2, layer 3. Those layers only coincide with the basal planes of the unit cell. Okay, so it is not very difficult to imagine that in case of HCP. And in the unit cell of HCP, there are 2 atoms. And how? Let us concentrate at this particular figure. Okay. Now this is the unit cell. This is 1/3 of the this particular hexagonal cell shown here. 1/3 of this, it is this. Now the 8 atoms at the corner will contribute 1, because each corner is shared between 8 of such figures. So 1/8 into 8, 1. And then this is the atom that is contributed by the second layer. So 1 plus 1 unit cell of hexagonal close packing has got 2 atoms. And what are the coordinates of this? But maybe I would want to clarify with you. The atoms at the corner are labeled as 0, 0, 0. Only one atom, because I have only one lattice point. Each of them contribute 1/8. Now you can ask me, madam, what is why this one, suppose I consider this as 0, 0, 0, then this one should be 1, 1, 1, and this one should be, you know, what, 0, 1, sorry, 1, 1, 0. But the only thing is all of them are equivalent position. And anyway, all of them are contributing 1, 8. So we denote them by one particular coordinates, and that is 0, 0, 0. Okay. Now, looking at this particular atom. Okay. If you try to concentrate on this particular atom, and suppose what I do is I press this atom. I want to show you now the C coordinate. All of you will agree with me. Suppose this was the 0 layer and this was the 1 layer. The C coordinate of this atom would be half. And that I have already written here. Now we have to clarify 1 by 3 and 2 by 3. Now suppose I press this atom. This is very hypothetical, but I press this atom to the basal plane. This is what it will look like, right? See, I have already decided it is half. Now, suppose this is the 0, 0, 0 thing, then coordinate of this particular atom would be 1 by 3 if this is x-axis and this is y-axis. Then coordinate, okay, either ways, x and y you can interchange, that doesn't really matter. But suppose I'm considering now, if I want to match it with this, I will consider, okay, yeah. So on x-axis, the coordinate is 1 by 3. And on this axis, the coordinate is 2 by 3. And c-axis that we have already agreed upon is half. So your hexagonal unit cell has got two lattice points. From now on, you will remember hexagonal unit cell has got two lattice points. The coordinates are given by 0, 0, 0 and 1 by 3, 2 by 3, half. Okay. Can we go to the chat box, Anura? Is it clear to everybody? Anura, chat box. Let me know. Type yes if it is clear, 1 by 3, 2 by 3, half, because these are the certain things that are not clear even after you read your textbooks. Okay, you will have to respond to me before I proceed ahead. Okay. Okay, I'll just repeat one more time. We were talking about the unit cell of hexagonal close packing. And I told you, now this is my hexagonal close packing. Let's say this is layer 1, this is layer 3. And in that case, this becomes layer 2. So if it is the C position of this layer is 0, the C position of this layer is 1, then C position of this layer is half. Okay. And I take my unit cell of hexagonal close packing as this one. This particular unit cell. I expand it here. This is how it looks like. Okay. Now I say this particular unit cell, if anybody asks you what are the number of lattice point in the hexagonal unit cell of hexagonal close packing, there are 2 lattice points. And what are those? One at the corner. One at the corner. Why? Because even though I can see 8 atoms at the corner, each of them is contributing only 1 by 8 to this particular unit cell. And the coordinates of the one at the corner is 0, 0, 0. Okay. Now we have to find the coordinates of the other lattice point, which is this particular atom. Okay. Now coordinate means x, y, z value. Z value we have already agreed upon that this second layer lies in between 1 and 2, equidistant from 1 and 2. So iska C value is half. Now we have to, z value is half. Now we have to find the x value and the y value. Now for that, just for a moment, hypothetically imagine that I have pressed this sphere to the bottom basal plane. Okay, this is how it looks like. Now I have to find the coordinate on x and y axis of this particular atom. So if you see, this is how I will find the coordinate. If this is x axis and this is y axis, it makes an intercept of 1 by 3 on x axis and 2 by 3 on y axis. Okay, so the coordinate of the second lattice point in unit cell of HCP is 1 by 3, 2 by 3, half. I hope it is clear now. Okay, but now there is, I mentioned one thing. I said your basal plane of this unit cell. And what are the basal plane? This is a basal plane. This is a basal plane. Basal plane of the unit cell in hexagonal closed packing coincides with the packing of the layers that we talked about, AB, 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 AB. Now the problem occurs in CCP. In cubic closed packing, the unit cell of cubic closed packing is an FCC unit cell. And what is an FCC unit cell? You have atoms at the corners of the cube and atoms at the face center of the cube. But now the interesting thing is, suppose this is that particular cube and these are the basal planes. Basal planes are the faces of the cube. These basal planes, they do not coincide with the packing of the layer in cubic closed packing. Okay, how does it look like? It looks like the layer, suppose this is the, I say the cubic FCC is the unit cell of the CCP, but the layers are packed in this way. Okay, if I hold my cube by two opposite corners, the layers are packed along the body diagonal. I hope it would be clear by this particular figure. Assuming this is a sphere of the first layer, A layer, this is the sphere, these are the spheres of the B layer. CCP is your ABC packing. These are the spheres of the C layer. This is again the sphere of A layer. Right, it falls directly below this, as you can see. But now my FCC unit cell, as you can see, is placed like this. Okay, this way. And now the planes are not coinciding with how your layers are packed. This is the point that I want to make. Okay. So this is one interesting thing. And easily all of us know there are 4 in FCC. How many lattice points are there? We have lattice points at the corner of the cube and each corner contribute 1 by 8. So corners contribute 1 lattice point and there are atoms on the faces of the cube. How many faces do we have? We have 3 faces. We have 6 faces. And each face contribute half. So 6 faces contribute 3 lattice point. So this is from the corner. And these are from faces. So total number of lattice point are 1 plus 3, 4. And what are the coordinates? The one at the corner, its coordinate is always 0, 0, 0. Okay. The one, now you will have to find the coordinates at faces. The faces coordinate would be, suppose this was my origin. Okay. The coordinate of this particular face would be x is half, z is half, y is 0. So half, 0, half. Similarly, this would be half, half. This is y is 0, 0, half, half. Similarly, you will have one more coordinate. Okay, so there are 4 lattice points in the FCC unit cell with these coordinates. please go, when after the lecture, just try to imagine an FCC unit cell and try to find the coordinate for all the 4 lattice points. And tell me if you have any problem, we will discuss it tomorrow. Okay? So again, just for your benefit, just one particular, in this particular slide, we'll again try to visualize. If these are the closed packed layer, this white layer, then this black layer, and again the top white layer. If it is an AB packing, you can visualize your hexagon like this, and your unit cell ka basal plane would be this. Okay, but in case of CCP, if you have ABC packing, the basal plane of your FCC unit cell does not coincide with the packing of the layer. Rather, if you hold your cube straight, your FCC unit cell not tilted but straight, then the packed layer are along the 1 direction. That means along the body diagonal. Okay. Now, all of us know that in the closed packed layer, for every atom of the closed packed layer, there are 2 tetrahedral holes. For every atom in the closed packed layer, there is 1 octahedral hole. So if n atoms are forming the closed packing, we have n tetrahedral holes, 2n tetrahedral holes and n octahedral holes. Okay. And how can you see your tetrahedral hole in the packing? Just imagine this particular green layer is the bottom layer and this orange one is the second layer. So this atom on the top and 3 green atoms at the bottom, this blue one is the tetrahedral hole. Similarly, if I have a layer above this orange layer also, then this orange atom would be at the bottom, and there would be 3 spheres above it with which it would be forming an inverted tetrahedra. So each atom is contributing to 2 tetrahedral holes, and that is why n atom 2n tetrahedral holes. Okay, and how can you imagine an octahedra hole? These are your 3 green atoms and these are your 3 orange atoms. This particular hole that you can see is an octahedral hole. 3 and then staggered 3, not eclipsed. In the center, you have an octahedral. Okay. So this is in your closed packing, of course. Now, how to imagine tetrahedral and octahedral void in hexagonal closed packing is not a very simple task. I would just like to tell you, okay, we'll spend 3-4 minutes on it. What is the time? And we'll see if you are able to visualize it. Else you try it at home and we can do it in the next class or in the last class that I would take for you. Okay. So, okay, let us see this. Imagine this is your first hexagonal closed packed layer A. This is your third hexagonal closed packed layer, again A. And this is B. Okay. Now, when I divided that bada hexagonal cell into chote unit cell, we know that there is one more lattice point at 1/3, 2/3, half. Okay. Now, how does the tetrahedral void look like? This particular atom will be joined with 1, 2, 3. This is a tetrahedra. Okay. And now this is your tetrahedral hole. Now what would be the lattice parameter coordinates for this tetrahedral hole? This lattice point we discussed some 3-4 slide earlier has got the coordinate as 2/3, 1/3, half. Okay. Now this tetrahedral hole is exactly over this particular lattice point. Okay. So what means the x and y coordinate of this hole are same, 2/3, 1/3. Now I have to decide what would be the z coordinate. So in a tetrahedra, along the c axis, along the length of the tetrahedra, the center of the gravity is closer, suppose this is the length of my tetrahedra. Then the center of the and this is the vertical line. The center of the gravity is this particular portion is 1/4 of this length. Okay. Now, if this point was C is equal to half, this point is C is equal to 1, then this point will be half, then 1, and you have to go 3/4 of this, which is 1/3. 2/3 are of course the x and y coordinate, and z coordinate would be 1/8. The z coordinate of this point would be 1/8. Similarly, this will form another tetrahedra like this. And this tetrahedral void would be 2/3, 1/3, and sorry, this is 1/8, and this was 3/8. Okay. So this is a little complicated, but just try to get a hang of it. And maybe we can discuss, spend some 10 minutes or 5 minutes more again on this particular thing. But till then, I would want to tell you that the coordinate for anions are 0, 0, 0, 1/3, 2/3, half that we have already discussed. The octahedral hole lies in 2/3, 1/3, 1/4, 2/3, 1/3, 3/4. And these are the coordinates for tetrahedral hole. These are a little difficult to imagine, and that is why hexagonal close packing is never explained in a lot of detail, but I would still want to do it. Maybe at the end of today's class, or let's say tomorrow class, we will spend some more time understanding the coordinates. Okay. Now, coming back to some normal structures, let us make a life a little simpler that you've already studied. We shall first brush up whatever we know about it. Okay, now as I said, we can define structure in 3 ways. And now for each structure that we'll talk about, we'll try to use all the 3 ways. First is you define how the unit cell looks like. Second is you define how in terms of the space sharing polyhedra. And fourth is the 3-dimensional view. Okay, now how can I define? The first one is rock salt structure, which is also famously known as sodium chloride structure. The unit cell is simple. Now, just one convention I would want to discuss now. Whenever we want to describe in the structure in terms of close packing, we say that anions form the close packing. Everywhere you will read this thing. Anions form the close packing and cations fill the voids, either octahedral or tetrahedral. But we'll spend a minute on this. Why is it so? Why don't we say? See, in a fluoride structure, we do ulta. We say that cations form the close packing and anion fill the void. Now, why is that so? That is because we consider the bigger ion to form the close packing, because the voids will be smaller. So the smaller ion will go inside. And most of the time, all of us know that anions are much bigger than cations. That is why the convention is that we say that the close packing is formed by anions and the cations fill in the voids. I hope this is clear. So, coming to the rock salt structure, we say that it is FCC of anions or cubic close packing of chloride ions, wherein your sodium ion occupy the octahedral holes. Or because Na and Cl are 1:1, it can also, now this was in terms of close packing. In terms of unit cell, chloride forms FCC unit cell, sodium ion occupies octahedral hole in the cubic unit cell. Now Na and Cl are barabar, so we can also say that sodium forms FCC unit cell and chloride occupies octahedral. Now, which brings us to one point. Okay, where are the octahedral hole in the FCC unit cell? I described you the octahedral hole when we have the close packed layer, but where are the octahedral hole when I'm talking of FCC unit cell? So, just spending a minute here, FCC unit cell matlab, you have atoms at the corner and you have atom at the face center. Okay, let's say these are chloride ion. Okay, now octahedral hole lies on edge centers and body center. Okay, how many edge centers do we have? We have 12 edges and 12 edge center. And each edge, the atom on each edge, how much does it contribute to one particular unit cell? This particular edge is shared by 4 unit cell. All right. So 12 into 1 by 4 is 3. But the one that lies in the body center is contributing completely to that unit cell. So 1 by this. So 3 plus 1, we have 4 octahedral holes in the FCC unit cell. Okay. So we can define that the chloride ion lies at the corners. It forms the FCC unit cell and sodium ion occupies the octahedral hole. When we say this, anybody who knows solid state will understand that sodium ion lies at the body center as well as the edge center. Okay. Now, so we describe the structure in terms of close packing. We describe the structure in terms of unit cell. Now, coming to the space sharing polyhedra. Okay. Now, you consider this particular cube. Let's say the orange one is chlorine and the blue one is sodium. This is sodium. Okay. Now this is one particular octahedra. This chlorine is surrounded by one sodium at the top, one sodium at the edge center, one sodium at this edge center, this edge center, this edge center, and this edge center of the unit cell which would lie in the front. That means each chlorine is surrounded by 6 Na. Now assume this edge. Okay. Now this edge will also contribute the octahedra which is formed around this particular chlorine. So NaCl can also be defined as three-dimensional arrangement of edge sharing NaCl6 octahedra. And now, because we know that we can interchange our Na and Cl also because they are equal in number, they can also be defined as edge sharing three-dimensional network of Cl Na6 octahedra. I hope this is clear. So we have described what are the 3 ways in which I can describe my NaCl structure. Okay. So coordination number of both Na and Cl in rock salt structure is 6, and this particular structure is adopted by KCl, AgCl, MgO and similar compounds. Okay. Now, if you try to see this particular unit cell, there is no point if I teach you everything that is written in the textbook. So let me just try to tell you some interesting tidbits. Okay. Now look at this particular cube. Okay. I have put the pink balls at the corner and the face center. That is, I say it is the FCC unit cell of chloride. Now, suppose I had put the black, I shift my, let's say this was the origin earlier. Now I shift origin to here. Okay. So what happens is once I have shifted origin here, this becomes my edge center. Okay. And I will have a black ball in front of it here, and that will become the second corner. Similarly, this has become edge center. Now this pink ball will also become edge center. Now the black balls will lie at the corner and face centers, and the pink balls will occupy edge center and body center. Only by shifting my entire unit cell by half. Okay. So now black ball form the FCC and the pink ball are occupying octahedral group. That means if you go and read the books, 1 or 2 of textbook may define NaCl as 2 interpenetrating FCC lattice of sodium ion and chloride ion. Now that will make sense to you. Why? By shifting my origin by half along any of the axes, either x-axis this way or y-axis this way or z-axis, by shifting it, I can make sodium as my FCC lattice, and now chlorine will occupy the octahedral voids, which are edge center and body center. Okay. Another interesting thing. I taught you about bases, and what did we talk about? We say that basis is an atom or the group of the atom. If it occupies the lattice point, I will be able to create my structure. Okay. Now, suppose I take this pair of blue and black ball as basis. Suppose I consider it as one big ball. Okay. And I just join. This will be joined with this. This will be joined with the black ball behind it. The unit cell which will be behind this, and similarly this would be joined, and similarly this would be joined with the pink ball behind it. You will notice, and suppose pink and black gives me a ball like this. I'm only doing this to make you understand. You will obtain a simple FCC lattice wherein this body ball, the big ball, would be at the corners and the face center. And now it is a simple FCC lattice where your basis is a group of, that means a pair of NaCl, that is one NaCl unit. Okay? And this is, we say, one unit cell is made up by 4 NaCl units. I hope this is clear. I would break for 1 minute and let me see the chat box if you have any doubt till here. Anurag, can we go to chat box, please? Any doubt? Please type in if you have any doubt. See, I need a fast response. If we don't interact, there is no fun in the class. Okay, I take it that everything is clear till this slide. Now, calcium carbide structure. I have taken this particular example because calcium carbide structure is exactly similar to sodium chloride structure. So, in place of calcium, in place of sodium, you have calcium, and in place of chlorine, you have carbide ion. Okay. Now, the only problem is this carbide ion is not spherical like chloride ion. It is an elongated ion like this. And when you put this elongated ion in place of spherical this thing, when you put an elongated ion in place of a spherical ion, what will happen? Your unit cell will also elongate along the C direction. And that is the reason, even though calcium carbide has a structure similar to NaCl, that is FCC of carbide ion with calcium occupying the octahedral void, it is still does not, NaCl had cubic symmetry. This particular cell has got tetragonal symmetry. Why? Because now, because of the elongated carbide ion, the entire unit cell has elongated along the C direction. So you have a tetragonal unit cell. Okay. Sphalerite structure, also known as zinc blende structure, it is taken by ZNS. Again, in terms of close packing, it is a cubic close packing of sulfide ion, wherein tetrahedral voids are occupied by the zinc ion. In terms of unit cell, it is an FCC unit cell where sulfide ion occupies the face-centered position. And when I say face-centered position, you should understand it is corner as well as the face centers. Okay. And the zinc ion, they occupy the tetrahedral voids. Now, where are the tetrahedral voids in the cubic unit cell? I hope you know. Suppose you have this cube okay, and I dissect it along this plane, okay, then along this plane, if I dissect it along this plane, it will be divided into two halves, the upper half and lower half. After dissecting it this way, I also dissected, let's say, this way. Now you will get 4 cuboids. I also dissect it now along this way. Now you will get 8 chota cubes making that bada cube. 4 cuboid at the top and 4 cuboid at the bottom. And center of each cuboid in an FCC lattice is a tetrahedral cube. Okay. And one more interesting thing. Suppose I'm concentrating only on the the smaller cuboid on the top half. Alternate tetrahedra would be inverted in their orientation. Now, what do I mean to say is, suppose this particular tetrahedral void is like this. Okay. Then the tetrahedral void along this particular distance would be edge sharing with this, but pointing in this direction. Okay. Now, why have we shown tetrahedra like this? Okay, this, if you can see this, it is like this. I mean, I could have shown it straight also. Now, this particular thing will show why is it like this? Because your FCC unit cell का जो faces हैं, they are not coinciding with the close packed layer of CCP. That is why tetrahedra point in this direction or in this direction. Okay, so I hope this is clear. Okay, my point here was basically coming back to the simpler thing. Your sulfide ion occupies the corner and the face center, and the zinc atom occupy the 4 tetrahedral voids. So the FCC atoms, that is a sulfide ion, they are contributing 1 from the corner, 3 from the faces, 4. And zinc ion, which are occupying tetrahedral void, they're completely contributing to only this particular cube. So 4. So we have 4 Zn and 4 sulfide. So the stoichiometry is Zn(S). Now counting the coordination number of zinc is very clear. It is lying in a tetrahedral void. So its coordination number is 4. Talking about the coordination number of sulfur. Okay. It is also very easy to imagine. Each sulfur is ultimately coordinated by 4 zinc. So the coordination number of zinc and sulfur are 4 and 4. Now, in terms of space-filling polyhedra, how can I define this structure? In terms of space-filling polyhedra, NaCl was edge-sharing octahedra. In terms of space-filling polyhedra, zinc sulfide is corner-sharing tetrahedra of ZnS4 or SZn4. Okay. You can easily see this if you try to imagine. Suppose this is one zinc and it is joined to this sulfur, this sulfur, this sulfur and this sulfur. Now, this sulfur is also joined to this zinc. Okay. So, 2 tetrahedra are actually linked by corners. So, it is a corner sharing 3-dimensional network of ZnS4 or SZn4 tetrahedra. Okay, what is the difference between rock salt and ZnS structure? Let us quickly brief that. Rock salt is FCC of 1 ion, other occupying octahedral hole. Sphalerite or zinc blend or ZnS structure is FCC of 1 ion, other occupying tetrahedral hole. In case of rock salt, it is favored by more ionic compound. We will study it in the next lecture. The ionic compound, ions, which are more electropositive and electronegative, they prefer to have as many ions around them as possible. Okay. So in case of rock salt, because the coordination number is more, so if you have a more ionic compound, Why we are comparing it? Because in both of them, the stoichiometry of cation and ion is 1:1. So why can't ZNS have a rock salt structure also? So there are many factors that control it. So as I said, rock salt is favored by more ionic compound and ZNS is favored by more covalent compound. Rock salt has got edge sharing octahedra. Zinc blend has got corner sharing tetrahedra. And the structure adopted would also depend upon the radius ratio, which would also be discussed. But then this is also an important factor that decides what is the structure adopted by your material. Okay, now cesium chloride structure, probably the simplest structure of all, and still people make fundamental basic mistake. First, talking about the structure, let's say if I'm talking of cesium chloride, anion occupies corner. That means only one lattice point per unit cell because each corner is contributing one by. And the other ion is occupying the center of the unit cell and that is also contributing one. So the formula is 1:1, cesium 1, chloride 1, cesium chloride. Okay. So coordinate of the anion or the ion that is occupying corner is 0, 0, 0. Coordinate of the ion that is occupying body center is half, half, half. Okay. Now, most of the time, whenever we ask somebody what is the lattice type of cesium chloride, invariably 99% people respond that it is BCC because it has a body center atom. Please remember this is wrong. We call a lattice as BCC only if the atom that is lying at the center is similar to the atom lying at the corner. Cesium chloride has got a primitive lattice. Okay. So now it can also be described as very interestingly uh, interpenetrating simple cubic lattice of cesium ion and the chloride ion. And how is that? Okay, right now let us say this is chloride ion. So I have a cube of chloride ion and cesium is lying at the center. Now suppose I shift the origin by half half half. That means origin मैंने यहाँ से ले जाके यहाँ move कर दिया. Now this comes at the corner. There would be another red ball in the cube above it. That becomes another corner. There would be another red ball in the cube adjacent to it. That will form another red ball. Similarly, in front, and on top, top, 4. So this will form another cube. Now, if you concentrate on that cube formed by red balls, this white ball will become the body center. Okay. So what we can say is, you must have read now, whenever you read that cesium chloride ka structure is two interpenetrating simple cubic lattice of cesium ions and chloride ion, it should not confuse you now on. Okay. In terms of space filling polyhedra, what is it? These are basically either the cesium 8 cubes that are sharing faces. Now, this is a face and there is another cube lying alongside it. If you consider this face, there is another cube which is in front of it. Similarly, we have faces along, cubes along all the 6 faces. So it is the face sharing cube repeated 3-dimensionally, wherein the center at place is occupied by the other ion. Okay, I hope this is clear now. Coordination number of cesium is 8. Coordination number of chlorine is 8, which is very much obvious from this figure. Okay, now coming to AX2 structure. These were all AX, NaCl, ZNS, cesium chloride. Now we'll come to AX2 structure, wherein the stoichiometry of the cation and anion is 1:2. So first of all, we talk about anti-fluoride structure. Why anti-fluoride structure? Because abhi tak the convention that we have followed is that the anion occupy the corner and in Na and oxygen, oxide ion is the bigger one. Okay. Now your blue ball is the oxide ion. It forms the FCC That is, it occupies the corner as well as the face center. And now Na are occupying all the tetrahedral holes. So when I say that oxide to ion form FCC, how many lattice points do we have? 4. And when I say that Na occupies all the tetrahedral hole, how many Na do we have? 8. So Na8, O4, which transforms to Na2O. This is called antifluoride structure. Okay. Coordinates, you would be able to guess if you know what are the coordinates of tetrahedral voids in the cube. It should be easy for you. Now, abhi tak the whatever structures we did, the coordination number of cation and anion was similar. But now here the story changes. The ion that is lying in the tetrahedral void, okay, because it by virtue of the fact that it is lying in the tetrahedral void, its coordination number is 4. But now the coordination number, that means the coordination number of sodium is 4. But the coordination number of oxide is 8. And how is that so? You concentrate on any one of oxide lying here. Let us say we concentrate on this particular corner wala oxide. What happens is, it has this red wala oxygen, sodium. There would be a sodium in the cell adjacent to it. There would be a sodium in 2 cells which are back at the back side, and it forms a 4 square. Similarly, 4 sodium in the 4 cubes that are on the top surrounding this oxygen. So the coordination number of oxide is 8. I hope this is clear. And how can we define it as? Now, it can be defined as, now earlier in zinc sulfide structure, when alternate tetrahedral voids were occupied, you had corner sharing tetrahedra. But here now all the tetrahedral voids are occupied. Okay. So you have edge sharing NaO4 tetrahedra. Until now, whatever we were discussing, the shape of the atoms around a particular atom. For example, Na had 6 chlorine, chlorine had 6 Na. Zinc had 4 sulfide, sulfide had 4 zinc. But here the story changes. So it can be described as 3D network of edge sharing NaO4 or edge and corner sharing ONA8 cube. This might be a little difficult to visualize. So you learn it as edge sharing tetrahedra of NaO4. That is easy. Okay. So this is about antifluoride structure. Coming to the fluoride structure, as the name suggests, it is inverse of antifluoride. Now, at the corner we have to have the bigger ion. Here calcium is bigger. Fluoride is a chotu ion. So calcium occupies the FCC lattice point. FCC lattice point, by now you should have it by heart. FCC lattice point means corners and face center, and all the fluoride, they occupy the tetrahedral voids which are 8 in number. Okay, everything else is similar to antifluoride structure. Okay. Now structure, these were the structure where the close packing was CCP. Till now, whatever we have discussed, whether it was AX or AX2. Now coming to the structures which have hexagonal close packing. Okay, HCP is a different ball game altogether. Even though everything is simpler, it is only AB packing, but visualizing the structure is not very simple in HCP. Okay, so coming to nickel arsenide. Nickel arsenide is equivalent of what NaCl was in CCP. What was NaCl in CCP? One ion forming CCP and the other ion occupying octahedral. Here, arsenic forms HCP because it is an ion and the bigger ion, and nickel occupies octahedral. Okay, so same as NaCl, but now the close packing is HCP. Okay, again, coordination number of both nickel and arsenic is 6, same as in NaCl for CCP. But here there is a little difference because now your AB and third layer is similar to A. Okay, so what happens is your polyhedra of arsenic. The polyhedra of arsenic is not. What is the difference between I would like to describe the simple difference. What is the difference between an octahedral and trigonal prism? Trigonal prism has also got six corners, and octahedra has also got six corners. Okay. If you try to imagine in terms of triangles, okay, when it is octahedra, suppose this is, I hope I'm able to show you 1, 2, 3. These are three corners of triangle. In octahedra, the bottom triangle would be staggered. I mean, if this corner is here, this corner will be in center of these two. They are not eclipsed, they're staggered. But when they are eclipsed, like in this is below this is below this, and this is below this, this is trigonal prism. A prism that is formed by two triangles. Okay. So what happens is, in case of NaCl structure, both Na had octahedra of chlorine around it and chlorine had octahedra of Na around it. But in case of nickel arsenide, arsenic has got nickel 6 का 6 nickel का trigonal prism. But nickel has got 6 arsenic का octahedra. It would be clear if you try to imagine that. See, this is nickel is occupying octahedral hole, okay? Now, this is your A layer of HCP and this is your B layer of HCP. And if you remember, they don't lie over each other. It has to be an octahedra, okay? But in case of arsenic nickel 6, this is, let's say, any one layer, A layer or B layer, because it is forming our HCP. The octahedral hole, they lie directly above one another. And since nickel is occupying the octahedral hole, they lie directly over one another. And that is why it forms a trigonal prism. Okay. Woodside structure, it is again ZnS, but zinc sulfide now is not in CCP, like in zinc blend or sphalerite. It is a hexagonal closed packing wherein HCP of sulfur and zinc occupies the tetrahedral voids. Okay. Polyhedra of both zinc and sulfur is tetrahedra. And it is a 3D network of ZnS4 or SZn4 tetrahedra. Now here the geometries of both the polyhedra are tetrahedra. Not like your nickel arsenide that one is octahedra and one is diagonal prism. So this is relatively easier. Okay, I had taken this figure on the separate slide because I wanted to show you where the tetrahedral voids are. But now doesn't seem we have a lot of time. So I may have to skip it. Unless you are interested, please write to me so that I can cover it in some other time. Okay, now few commonly known structure that we should be knowing. Titania is formed by octahedra hexagonal closed packing of oxygen. But what happens is, suppose I have two oxygen. How many octahedral hole will I have? I will have two in octahedral hole. Okay. But the stoichiometry of titanium is 1. For every 2 oxygen, I have 1 titanium. So this much is clear to me that only half the octahedral hole will be occupied by titanium. Okay. So exactly this is the structure. It is a distorted HCP of oxygen wherein your titanium, it occupies half the octahedral side. But how are those half occupied? That makes it different. Those half are occupied. Suppose you consider you have the layer AB. In between you have octahedral hole ka layers. Okay. Suppose this is a layer of octahedral hole, one layer. In this only alternate rows are occupied. That means if this particular octahedral void is occupied, the one adjacent to it will not be occupied. The other one would be occupied and then this one would not be occupied. Okay. So this is how what we get is, we get octahedral holes joined by corners in AB plane and joined by edges along the C direction. This is the structure of titania and this is how the 3D network is formed. Okay. It won't be very clear the first time I'm telling you, but you'll have to probably go back to this to understand the difference. And you will understand it more now when I tell you about the next structure, CDI2. Same thing. Iodine is forming distorted octahedral packing. Like what oxygen was doing for titanium. Here also, half the holes are occupied, similar to titania. Then what is the difference? In titania, every alternate hole was occupied and the adjacent was unoccupied. Here the interesting fact is entire one layer of octahedral hole is occupied, next complete layer is empty. Third is occupied, next is completely empty. And that is precisely the reason why cadmium iodide has got a layered structure. Okay, suppose these are all iodide ka AB layer, and in between we have octahedral voids. Only one layer is occupied, this layer is empty. This layer is occupied, this layer is empty. So CdI2 can easily be cleaved into layer. This is how your structure is related to property. Why is CdI2 easy to cleave? Okay, I hope now on you would be able to answer that question. Coming to CdCl2, similar to CdI2, but here the chloride ion occupier forms the CCP packing and not the HCP packing. Cd2 plus occupy alternate rows, alternate layers of octahedral holes. Okay. Now, just one simple thing I would like to discuss. Okay, and then we will end this lecture. We had silicate structure, but maybe we will skip silicate structure. Okay. Rb2O, you know, as we go down the alkali metal, what do we have? Lithium, sodium, potassium, then rubidium, then cesium. Okay. Now Na2O, K2O, Rb2O, all of them form antifluoride structure. Antifluoride is your oxygen form the cubic close packing and your cation goes and occupy the tetrahedral voids. And then you have tetrahedra. अगर मैं space sharing polyhedra की बात करूं तो tetrahedra share faces or edges, sorry, edges, not faces. But cesium 2O does not form antifluoride structure. Can you think of a reason for this? Just imagine what I just said. In case of antifluoride structure, you have edge sharing NaO4 tetrahedra. Okay, I'll get back to the answer straight away. Maybe you will not be able to think at this particular point, but you should keep these things in mind. Tetrahedra are smaller polyhedra. Okay, when they share corners, suppose this is the center of my atom, this is the center of other atom, and this is one edge of this tetrahedra, this is one edge of this tetrahedra. They are joined by sharing corners. Okay, now these atoms are far apart. Suppose I join edges, they will come closer. Suppose I join faces, they will come further closer. Okay. Now, the atom which is sitting at the center denoted by these 2 points, they will be very close if my tetrahedra are sharing faces. They would be relatively far apart if my tetrahedra is sharing only edges. And they would be very far if my tetrahedra is sharing only corners. Okay. Now, cesium is a very big ion. In antifluoride structure, the adjacent tetrahedra, they share edges. And 2 cesium, it's a bigger ion, coming close together will make the structure unstable. That is the reason that even though Na2O, K2O, Rb2O, they crystallize in antifluoride structure, cesium-2O is not happy in antifluoride structure. See, so there are many factors that control, even though the formula is same, even though they belong to the same family, alkali metals, how different things control the structure that is adopted. Okay, so I'll finish over here. We have not had a break. Thank you for bearing with me. The structural classes are not very easy to understand. They are very much better if we are face to face, because I can make you understand how the things are going. But whatever best we can do. So anything if you would want me to repeat, you can also mail me, as I mentioned in previous class. What is the difference between HKL and HKL? No difference, Ankur. It is just that when you use, can I get a wide screen? Okay, when you say, suppose you write something and you send me this. Okay, what I will understand from this is that Ankur is trying to tell me a set of lattice plane whose Miller indices is this. And if you send me a number covered by square bracket, what I will understand is that Ankur is trying to send me direction. These are the Miller indices of a direction. These are the Miller indices of the lattice planes. Okay. And if you have family of equivalent lattice plane, you represent them by this. These are just conventions. If you have, family of direction, you represent them by this. I hope this is clear now. Those things are covered. Okay. So I hope HCP, octahedral and tetrahedral coordinate. Sudeep, I would really love to do this, but what we can do is, was that for me? HCP, octahedral and tetrahedral. But Sudeep, maybe in probably some next class, if we try to get some time, I'll get a better figure and try to explain it, okay? Anything else? Anything you want me to repeat, please mail me so that I would also know how much portion of the syllabus I would be able to cover. Because I would really love to clear your doubts rather than covering many new topics unnecessarily, actually. Okay, then in that case, good evening and have a good day. And we shall meet on Friday again at 4 o'clock. Thank you so much.